Hello, Math 31. Math 30-1, sorry. So this is a continuation of our unit that we started just before the break. As you'll see that I'm going to go through the first section again, just to get yourself a refresher of why certain things are, what are the characteristics of an exponential graph, and then we're going to be talking about logarithmic functions as well. So let's get at it. At any point, like if you have questions, remember that I'm going to have office hours, physics in the morning, math in the afternoon. If you have questions, log in. If you can't make it to the one in the afternoon, you can log in the morning one just to see if there's too many kids doing physics at that point. Then try to log in the afternoon if you can. If there's not that many physics kids, ask you a math question at that point. I'll see if I can answer it. So we'll try to figure this out as we go. It's brand new situation that we have here. Probably going to run into the same kind of problems I had on the whiteboard where my thing's going to flip up and down because I'm using the same kind of technology. But this time I'm going to be using a little tablet system to do this. So I'm sorry if I'm looking down as I go through these notes here. We'll figure it out as we go. Yeah. So exponential function. So an exponential function, as we remember, if we recall, is a function, a little dissimilar than what a polynomial is, that it's in this form where it has a base at the bottom, and the variable is the exponent. I'm sorry for the writing on this. I'm just trying to get my groove here. I'm trying to figure out how the handwriting is going to look on this little tablet. It's going to be a little bit different than on the screen that you saw in front of the class here. So you just have to remember that the base, to be an exponential function, to make sure it's an exponential function, just cannot be 1, because if it is 1, then you just have a straight line at y is equal to 1. And the base has to be greater than 0. So these are these two conditions here that, as you can see, are kind of written up here. So you have these two main conditions here. Okay. So let's look at this guy. This is an exponential function because you can see that the base, the c value, is 2. Let me just scroll down here. Okay. You can see the variables in the exponent like it should be. And that means over here, when I put my x values, these x values are going to be in the exponent where the base is always going to be 2. So here I got 2 to the power of negative 2. Here I got 2 to the power of negative 1. 2 to the power of 0, 2 to the power of 1, and then 2 to the power of 2. We can just quickly do the math. So remember that the negative exponent just means take the reciprocal of it, change the exponent to a positive number. Everything else stays the same. Like if it had a negative base, it'll have a negative base. That's fine. We're not supposed to have negative bases, but in just case if we end up having one of those in the future, so I got 1/4 there. There's going to be 1/2. Anything raised to the power of 0, remember, is equal to 1. That's equal to 2, and this is equal to 4. So I'm going to just plot these points on the graph here. Let's see how this turns out. We could do some extra mental ones here, like if my x value is 3, that'd be 2 to the 3, so that'd be 8 there. So you can see that this part of the graph is going to be increasing as you go from left to right. And because of that, we call that, oops, sorry, I'm moving the thing around by accident. We call that an increasing graph. We also call this a growth function because of how we read it from left to right, the graph is going up. Now, if we continue the pattern backwards here into the negative exponents, to much larger negative exponents, you're going to realize that as I go back further, say I go negative 10, you get 1 over 1024. If I go into like negative 100, for my x values here, I'm going to get a really small number. Let me just punch my calculator here. We get something times 10 to the negative 31. So because of how small it is, we can almost say that this is approximately going to be 0. Now, when we think about this, we also have to think about, are there asymptotes? Is there a line, in this case, a horizontal line, that this can equal 0 or can equal? And we already know from previous courses that, or our previous class before the break, that the y asymptote, or the y is equal to 0, was the horizontal asymptote here. And the reason behind that is that you want to find out what this cannot be. And to figure out what this cannot be, you have to, well, try it out, see if it can equal 0 or not. We're just going to look at that. We can kind of see up here that it's approaching 0, but it's approximately 0, but it's not actually equal to 0. This is not equal to 0. Okay. It's kind of weird to say 0 is not equal to 0. So we can think, okay, this is 2 to the power of x. Can this ever happen if we have a base equal greater than 1? No, greater than 0, actually. Well, if you think of, okay, it seems like these negative exponents are the ones that are going to cause the way you can get closer and closer to 0. So let's just put a negative exponent in there. So this would be 1 over 2 to the power of x. So I'll just change that negative exponent into a positive exponent. So it's a negative here. But then you look at the top and say, okay, the top is 1. It will always be 1. It'll never be 0. Like there's no way for this ever be 0. And the bottom will always be a number. So a number not equal to 0 divided by another number not equal to 0 will always be a number. So this can never be 0. It just doesn't work out. The only way to ever make this equal to 0 is for the top was 0. The bottom was 0, then we have a divide by 0 error. And that's why we don't have, if you go back here, the bases of being negative numbers, because we might have a, or even 0. The base cannot be 0 because we could have a divide by 0 error. Anyway, so if I graph these other points in here, you can see that they're going to get closer and closer to the x-axis, but they'll never touch it. Now this is where I gotta draw that out. Okay, looking good. Now you can see over here, I got my base now is equal to a half. So let's say that's a half. That base is equal to half. I can exponent of x here, so I can put in here. I can go 1 over 2 to the negative 2, 1 over 2 to the negative 1, 1 over 2 to the 0, 1 over 2 to the 1, and then 1 over 2 to the 2. Yeah, so I plot all those points in there too. So anything raised to the power of 0 is 1. This is going to take the reciprocal. So this is a 2. This will take the reciprocal after squaring it, or you can take the reciprocal first and then square it. They'll end up in 4 either way. And here we got a half, and here we got a quarter. Okay, so we got, let's put some of these points in here. So I'm going to go back here. X equal to negative 1 over 2. X equal to negative 2 over 4. You follow the pattern. I'll have 8 again here. And then if I go forwards, I got a half, a quarter, an eighth, 16th. You'll notice that, maybe if I do this better, that we have another, oops. Okay, we're just going to fix that. So bear with me because learning this technology and it's a little bit trickier than drawing on the whiteboard. Okay, so you can see that this is going to be a decreasing graph, and sometimes we call this a decay graph or other terminologies and other subjects as well. So you'll notice that both of these graphs, as long as the base is the proper base, my exponent can be whatever you want it to be. It'll always work out. So I can have XER for both my domains for both of these graphs. Okay, my range. Now you notice that this graph can never be less than 0. It can't be equal to 0 either by the same proof that we have down here at the bottom. So my range has to be greater than 0, not equal to, and it could be any other point in between. Let's see if we have a nice continuous line there. So y has to be greater than 0, and y. Okay. X-intercepts is because it's the same logic that we have down here, where this can never be equal to 0. Can never be equal to 0. We have no x-intercepts. And you notice our y-intercept, whenever our x is equal to 0, since there's nothing in front, there's no value in front here to multiply with after the fact, after we do the exponent. If I did that math, this is always going to be 1. If there was a letter or a number in front, and we did the math, this piece will turn into a 1. Then you have 1 times a, and this will turn into a. And that's important for later on. If we put something in front, it's just like the a from before. That's just going to be a stretch factor. Okay. So same idea over here. We make this equal to 0. Let me put a 0 there. We got 1 out of that. Okay, so we have an x-intercept of 0, 1 for both those points. Okay. Let's quickly do this. Okay. So just a quick little shortcut if you ever look at the base value. So you notice our C value, we're going to look at the C value. It's increasing, or we consider it an exponential growth function if our C value is greater than 1. So we get this graph that will be going upwards from left to right as we increase the X values. We consider it to be a decreasing graph. It's between 0 and 1, and that's when we get our decay graph. So it's going to go the other way. Okay. You notice that we're not including 1, we're not including 0, because those are not exponential functions. And they would be considered other functions, or linear functions, or just a constant function, depending on which C value you picked. All right. So the graph. So what graphical characteristics are the same between all of these? What we notice up here, if we just do a little scroll up here, the domain is the same for both these graphs. The range is the same for both these graphs. The x-intercepts and the y-intercepts are the same for both these graphs. And what really changes, the only thing that changes is basically the shape of the graph. And then we discussed this in class before, but the shape of these graphs, if you look at very carefully, they're just reflections over the y-axis. And remember, in our transformations, we can achieve that reflection in our y-axis by doing a negative x in my f of x notation here. So we can just quickly verify that this actually will give us the same result if, say, my f of x started off as 2 to the power of x. All right. So my new graph, let's just call this one here, let's call this one g of x, is just going to be the same as this function here. We're going to put a little negative x in there. So remember what we did before. If it's inside the function like that, we replace all the x values. So we got 2 to the power of negative x, and this will be 1 over 2 of the x. And if you want to, you can write this as 1 over 2, sorry, all to the power of x. So you can bring that exponent out. Because 1 to the power of anything is just going to be 1. So you can also just treat that as it has an x on it if you want. And then since they're both being divided and they both have the same exponent, we could just group them together. Yeah. But what graphical characteristics are the same? That's a little bit beside the point, but we have domain, we have range, we have x and y intercepts, and our asymptotes. They're all the same. Okay. Yeah. So what we remember, so if we know those are the characteristics are the same, we can look at these graphs here and just quickly determine in this form, and you notice in this form is not included an a value in front of this. So we don't have this right now. So we can just treat this to be 1. And you can see that quickly by looking at the graph here, that it is 1 because that's where the graph is on the y-axis. Because of this situation, we could just say a is equal to 1. Yeah. So if I want to know what it is, you can look at, usually you just look at the first point at 1, and you can see it's 1, 6, and over here is a negative 1, 3. But this is an increasing graph. So what I know about this increasing graph is that that C value that we're looking for there has to be greater than 1. And this one's decreasing. So it's got to be between 0 and 1. Yeah, so let's look at this first graph I want to figure out. So I want to figure out in the form y is equal to c to the power of x. And we're just going to put any point. It doesn't matter. You put any random point in there. So let's just pick this point right here. And we're going to say that when x is equal to 1, this graph must equal 6. And this is going to be c to the power of 1, which is going to be c. So c is equal to 6. So my overall graph is going to be y is equal to 6 to the power of x. And you can see that my c value is greater than 1. And it just worked out. And if you want to test the other point, you can. So you could think, okay, if my x value is 2, so yeah, if my x value is 2 here, 6 squared is going to be 36. So it worked out just fine. So this point verifies that point there. So this graph is an exponential function based on this. So we can go over here, we can do the same thing. Remember, this is just like transformations. If there was an a value, you'd use the 2 points to solve for it. You can have like a system of equations, and we can solve for either a or c, or b, or h or k, depending on what we have. So if we did treat this as if it had an a, and we didn't know exactly, but we know the a is supposed to be 1, if we did treat that, we can actually just go through and say, okay, well, we have this point here. If I put a 0 in, I should get a 1 out. Okay. So if I put a 0 here, I need to get a 1 out. Anything raised to the power of 0 is 1. 1 times a. So a is 1. That just confirms our original hypothesis or estimation that we had there. So right now we have c to the power, or c is equal to, or y is equal to c to the power of x. And now we're just going to put in our other points here to solve. So let's see, if I put a negative 1 in, so I'm going to pick this point here, I should get a 3 out. Remember our negative exponents, take the reciprocal. We just rearrange this, we times the c up, divide the 3 down. C is equal to 1/3. So my equation is going to be 1/3. Put that in brackets, to the power of x. Okay, that's my final equation. Okay. Not too bad. If we have an a value, we just use the a value. If we have an a value, notice that the y-intercept is going to be a different value. Okay? And you can see that in these questions here, we're going to have an a value. So like our starting position, we can almost just call that the starting point. It's the initial amount. So where does it cross the y-axis? The y-intercept. Okay. So I want to model this. I want to create something that says something if I'm increasing by a rate, increasing. I like this idea where it says increasing. That means my c value has to be greater than 1. But this says only 90%. So remember 90% in decimal. Let me just fix that. Come down here. Back in the right spot. You'll notice that, yeah, we're running into the same problem we had before. Oops. All right. Remember 90% in decimal is 0.9. So my c value can't be 0.9 because that would be less than 1. It would be a decreasing graph. But since I'm increasing, I'm going to have to add the original 100% from before. So we have 100% plus the 90 on top of that. So this is actually going to end up being, with my c value, 1.9. And there's a few other things that we can do. If it's interest, we'll have to do something with the interest as well, regarding compounding rate periods and stuff. But we'll worry about that when we get to those ones. So my equation here is going to be y is equal to. Now, I like using the letter y here for my variable. Sometimes you wanted to relate it to what the equation is. So maybe you can say y is equal to n is the number of bacteria, or b, or something else like that. But we'll just stick with the standard y is equal to here. We have an initial amount. I'm assuming that it starts off with 1 bacterium. My initial amount is going to be 1. So we have 1 times 1.1 to the power of x. Okay. I'm just going to put in here what x stands for, where x is the time in hours. I know it's going to be in hours because this is yours per hour. Okay, so it's going to be key for later on when we're trying to solve this. And it's like, how long will it take? And maybe you want to specify how long is it? Is it days, hours, months, meters? Like, so this is just going to tell us what units it's going to be in. All right. So to do this one, we're going to graph this because we haven't learned how to solve these kind of equations where we have an x value in here, and we want to make sure that it reaches 1,000. So I want my y value to be 1,000, and I want to know what x value I'm going to have to put here to make that work. Okay? So we can graph this out. And if we graph this out, and put a nice little scale on this, if we got x, here we have y. I should put my scale. You can see that I think there's a little tiny scale on there. They give us a little window here that we're going to go up by. So it looks like we're going up by 5s. So 5, 10, 15, 20. And over here, it looks like we're going up by hundreds. 1, 2, 3, 4. Probably want to go a little bit more than that. So 2, 4, 6, 8, 10. No. I don't know what we're going to go up here. Maybe by 400s. So 400, 800, 1200. All right. 4 plus. Yeah, that makes sense. Okay. And then 1600. Okay. So how is this graph going to work is that, okay, so we put in some data points in here. You can put this into your calculator where if you're going to graph in your calculator, you make y is equal to one side, and then you make y1 actually equal to the graph, and then you find the intersection point between the two graphs. And I'm going to have to sketch this by hand because I don't want to pull up my graphing calculator here on the computer. So I'm going to draw a line here for y is equal to 1,000. And then we're going to draw a graph here. And we know that when x is equal to 0, because my a value is 1, I'm going to have a point way down here at 1. And then when x is equal to 2, we have 3 point something. And when x is equal, or sorry, up to 5, it's equal to 24 or something. It's 200, 124, still quite down here. Then if I go to 10, I'm at 600 and something, so 613, right about there. And then when x is equal to 15, I'm going to put that in my calculator, I got 15,000 something, something, something. So this goes off quite crazy here. So maybe I'll just redraw that line. And it's going to scream off and not even hit this 15 within our window. So we're looking for that point there. You can graph the two. What do we get here for our answer? Let me just plug in my calculator here quickly. A window and a nice y max spot here. So what did we decide? 12. Okay. So the graph doesn't quite face my window. I'm going to change my window just quickly here up to 20. Okay, this will give it a little bit of time to find an answer. But we're going to have x is equal to something. Oh, I see my intersection point there. So second trace intersect. And we get an x is equal to, if I move my hand, 10.7, 10.78, or 10.76, so that's about 10.8 hours to reach the 1,000 bacteria that we wanted there. You can see that's just slightly past the 10. Okay, let's keep on going. Yeah, just want to see how much we had to go on to this one here. So this is going to work the same way, right? Go right to the exponential function. I'm about to read a little bit ahead here, but since let's talk about percentage here, we can always just say that our initial amount is going to be 100%, or if you want to, you write it as 1.0. So if you pick either one of these two, you just have to know what your final answer actually means. If you start off with 100%, and you get like 0.5, it doesn't mean that you have 50%, it means you have 0.5%. Or if you start off with 1 and you get 0.5, that does mean 50%. So you just have to know if you're going to use one of these, which one you're actually going to use and what your answer means. So let's say I used 100% one here. So I start off with 100%, and we're decreasing this time. So that means my C value is going to be the 100 that we start off with minus this 12%. And I end up with 88%. And you can see my C value is less than 1, so I'm going to decrease in graph. So I'm going to put that in here. And that's my equation. That looks pretty good. And then I want to know after 6 years, and this is per year already, so where X is in years. I like to just specify this later so that I know later on, like what if this said in 6 months, and then I had to change it to years. Okay, so this is going to be 100%. And then we got 0.88 to the power of 6. And then you just punch in your calculator times 0.88 to the power of 6. And I'm left with 46.4% at the end of that. 6 years there. Okay, so let's see what we have here. Okay, we're going to do the same thing here. We're going to create a graph or equation. We have 20 rabbits to start off with, so I know my A value is 20. The population triples every year, so that means my C value is going to be 3 this time. Okay. We'll talk about this later on, but this the C value is how much you multiply by each time to get to the new answer. we always take the previous answer and go on. And you can see that from the graphs way at the very top there, that every answer was just 2 times 2 times 2 times 2, because the base value was 2, or half times a half times a half, because the base value was a half. Triples each year for 5 years. What's the population for 5 years? So we know our x is going to be 5, assuming x is in years. So I'm going to create an equation here. So I start off with 20. My c value is 3. And I'm going to put a 5 up here. It doesn't actually specify create the equation. So I'm just going to punch it in my calculator. And you get 4,860 rounds. All right. Obviously, that's an oversimplification of a population growth model, but that's fine. We can oversimplify for math just for the fun of it. All right. In this question we talked about before as well, before the break, is that household detectors, and every detector has a little bit of radioactivity in it to detect the smoke. If you ever take physics, we'll talk about what that actually means. It's just the smoke stops the radioactivity and stops the circuit and the thing goes off. But you have here, we've got half-life. That's the key word here, a half-life, because it says half-life. We're going to assume our C to be a half. Right? You can model these without using C to equal to half. You can have a more irrational looking number for the base. But most of the time we use, because it says half-life, the best case is to say our C is equal to half. Over here, it tells us what our starting point is. So we know our A is this 200 micrograms. Right? That's a little mu symbol. It's a Greek letter. Now, the half-life part here gets a little tricky. And there's a half-life formula on the formula sheet that specifies this. It says y is equal to, I think it says A to the half, and then there's T over T, or T over T, P, or there's a little half here. And the bottom number is the half-life period. I mean, how long does it take for it to be half of what it was before? So if I had a little graph here for this.
Mrs. Nivens, if you are in the building, could you please make your way to the office? Mrs. Nivens, to the office. Thank you.
Sorry for this. That's probably going to happen quite often in this class. Okay. So I got a t value there for time. That's just the time on the top. That's what we're talking about here. Okay. And then we'll just call this y because I don't have anything else for it. So let's say I start off with 200 micrograms here. The time it's going to take to get to a half, because this is what a half-life is, to get to half what it was we saw, I plot a point here. So we start up here, plot a point that's half of that. This time is 432 years. It's the time to take to get from one half of what it started off with. And then if I go down to 50, which is a half of 100, so I'll plot another point here, about there. This time, from here to here, is going to be 432 years as well. So this time, if I start from 0 way over here, is going to be 864 years. And then half of that would be another 432 years, et cetera, all the way down. So I do have this decay graph that looks like this. It starts at this point up here, so that's why our A is 200. So the equation that we're going to write here is going to be 200. And if you want to write the units, you can write the units here. 1/2 T. The problem is we don't know what T is, but we do know what the half-life period is. So that's this number on the bottom. So that's going to be in years. Now, you can write it this way. You can write an X here, but then you have to specify what the X stands for, like I've been doing up before. If I say where X is something. Now this way, if you just write it this way, time is time. You can say time because we're talking about in years here. We can say T is in years, not hours, because some half-life questions you might see in hours or minutes or seconds and stuff. You just have to know what kind of time we're talking about here. So this is more or less what my equation is going to be. And if you graph this, you would get this general shape. You just have to make sure your window kind of fits nicely. Looks pretty good. Yeah, and we're going to solve these later on, so this is probably the best way to do this. And this divide by period part is actually pretty important for the interest kind of questions as well. Yeah. So let's check out some other questions here. All right, so here's a half-life question. You can see that this half-life question is slightly different because the time here it says time, and then it goes 2, 4, 6, 8. Now T is 15 interval days. So this 2 here doesn't actually mean 2 days. It actually means 2 times. So that's actually 3 days. And say the 6 doesn't mean it's 6 days later, it's 6 times 15. So 6 times 15 is 90. Okay, so what's the initial amount of the sample? If you look up here, that's the initial amount, it's in grams. So my initial amount is 1 gram. What does this value approach as time increases? As this keeps on going and going, what's going to happen? We know it's approaching 0, right? It's approaching 0. Mass is equal to 0. You can see that I'm using m because we labeled that y-axis as m, and over here they labeled the t-axis or the x-axis as t. So we're approaching 0. We're not going to get to 0, but we're approaching this number. So this is like my asymptote. Let me just write that down. Okay, what's the domain of this? Well, because this is a real-world question, our domain has to reflect these real-world questions. So, well, actually, I'm not going to use x here. I'm going to use m. Let me just erase that m. Right? Or there's the x, sorry. M. So this is my domain. I'm using m's here. But my m starts off. Oh, sorry. We're doing our domain first. Our domain is time. Okay, so our time is our x-axis here. So we're starting off at 0. It could equal 0. We could start off at 0. And then it's going to go on forever. So that's just a poor way of writing that. T is greater than or equal to 0. T-E-R. Okay? Our range of a function, that's our m values. It's going to, the lowest number is going to be, it's approaching 0, but it can never quite reach 0. So it's not going to be equal to that number. But it starts off at the highest point here at 1, but it'll never be greater than 1. So, but you can equal that number though at 1.0. And your mass can be any number in between. There you go. So we got our domain and range. What's our exponential function here? So we just write it out the similar way that we wrote before. I won't use y though. I'm going to use m. So my mass is equal to my initial amount. 200 was the last question. So 1 gram times a half t over, and then whatever a half-life happens to be in this question. It says here a half-life of 15 days. And you can see that worked out here. 1 down to 0.5 in one interval here. So I can put 15 here, where t is in days. Actual days, not these interval days up here, but an actual day. This is a much better equation than using x or using the t values here and then try to change it later. Yeah. Now, to do these kind of questions, we have to do it by graphing, but we want it to be 1/30th of its original mass. Since I started off with 1, 1/30th times 1 is 1/30th. I'm going to change it too much. So that's what I want my equation to be equal to. And then we're going to solve for t here. So we can graph this out. Just make sure you're changing your window properly. And if I did that, I can load up Desmos here. Quickly do that. Okay. So I'm going to type in our first equation. I want it to be 1/30th. Oh, maybe I should make that equal to y first. Right? Y is equal to 1/30th. So I got my line. You can see there's my line going across the screen here at 1/30th. And then I'm going to make my next equation. What would I say? It was 1 to the power of 1/2, or to the power of x over 15. And we're just going to zoom out of this graph here. Maybe zoom into the axis here a little bit. You can kind of see over here, cross is right there. So it says about 73.6. So we just solve for x, which is our t value from before. Let's go back here. So t, t is equal to 76 point. What would we say it was? 76 point. 73.6, sorry. days. How much rating is left after 80 days? So let's go with the mass here. So here, this is a little bit easier math. Just telling us 80 days here. So just put a 80 here at the top, and then just punch in your calculator. That's not the right number. Gotta make sure to put brackets and everything. So, how much radium is left after how many days? We have 0.025 grams. 0.05. Okay. What equation? How would the equation change? The A value would now be 12 grams. So I have 12 grams to the power, or times a half to the power of t over 15. Would the equation change if this was a growth function instead of a decay function? Yeah. You can kind of see what would happen there. To be a growth function, your C value would have to be your C value would have to be greater than 1. In this equation, you couldn't model this with a C value greater than 1 because the graph is a decaying function. I guess you could change it to have a negative exponent. They kind of built in already, so that would do the reciprocal for you. But yeah, it would change considerably. I'm not going to bother filling this in because you can't really model it with a growth function in the first place. All right, so that ends off our first lesson. Then we're going to start some new stuff on the next video. So everyone should have these notes already. You just follow along, and I'll be posting assignments as we go as well that you can complete. We'll put the answers up for those assignments online. And throughout the week, maybe at the end of the week here, we're going to have more quizzes and more formative stuff that you could do throughout to help yourself with your learning, because you're going to need this stuff, and when you write the diploma, you're going to have to know this material as well. All right, I'll see you next time.